back. Okay, so let's go ahead and get started. So I suppose the initial announcement I have is just regarding any due dates coming up. So there's a homework due tonight on probability rules. I saw some people have already knocked it out. So that gives me an impression that it's pretty quick to breeze through. So if you haven't done so already, please make sure you do the probability rules homework. Additionally, the corresponding quiz that refers to the least squares regression and the probability rules, that quiz is due Friday. And the discrete random variables homework that we finished in class on Monday, that is due this coming Monday. So those are the only 3 assignments you have to worry about for this class moving forward. Besides for that, that is pretty much it. And whatever leftover time we have at the end of class, we'll go over the exam. The remainder of the exam. I didn't get to cover every question. We'll try to finish that up at the end of class. Does anyone have any questions before we get started? The 2 people who just walked in, your midterms as well. What's your name?
Shelby.
Shelby.
Fraser.
Oh, Fraser. Did you already get yours?
Yeah, I did.
Oh, do you want to? Yeah.
No, it's
Okay.
And those.
So, all right. So let's go ahead and get started with the new material that is referring to binomial probability distribution. So with this section, we're dealing with a specific type of discrete probability distribution. So it's a specific type. And for these, really, these experiments are specific in the sense that their outcomes are Boolean. And that might sound like a weird word, B-O-O-L-E-A-N. Boolean simply refers to 2 values. Generally, sometimes they're called yes or no, sometimes it's true or false, sometimes it's success or failure. But we're looking at things where the outcomes are just either does this satisfy some condition or does it not? So simple as that. But as we dive into this a little bit more, there are some conditions that need to be satisfied in order for an experiment to be considered a binomial probability experiment. The benefit of knowing that your experiment is a binomial probability experiment is that, as we will see later on, we get a lot of nice properties out of that. Some formulas and some nice calculator tricks that we can utilize that could give us a lot of very useful information. So that's why it's worth trying to determine this if we can. So an experiment would be considered a binomial experiment if the experiment has a few of these properties. Mainly, we're going to be looking at the top 3. The first thing is, before you even start the experiment, you need to know the number of times that you're going to be, running the experiment. And each time you run the experiment, that's called a trial. So you need to know ahead of time how many trials you are going to be having in your experiment. And the trials are independent. So the result of one trial will not affect the other ones. And additionally, for each trial, so this is kind of the point I mentioned earlier, there's they call it 2 mutually exclusive outcomes, which means that you're either going to get a yes or a no, not anything in between. And in this section, they call it success or failure. Does this person satisfy this condition or do they not? And they just get lumped into one of 2 categories. And the last one, not really going to focus on that one too much. The probability of success is the same. Just noticed, didn't even notice that in the last class. Is the same, is the same. Oops. Is the same for each trial of the experiment. So every participant has an equal likely chance of having a success or failure. And we also can attach a random variable to this experiment like we did in the previous section. So again, we called that random variable capital X. And so if capital X represents the number of successes, if we run this experiment lowercase n times, capital X, we can call that a binomial random variable. And we'll see some of the repercussions of this a little bit later. But for now, with all of these conditions I just threw your way, let's go ahead and look at example 1, which will sort of distinguish what a regular experiment, how a regular experiment may differ from a binomial experiment and what it may be lacking. So we're going to determine which of the following represent a binomial experiment. So the first situation we can visualize here. A basketball player who makes 80% of his free throws. That player is asked to shoot free throws until he misses. And then they record the number of free throw attempts. So the first condition is that the experiment is performed a fixed number of times. Is that true or false? Sounds like it's false. If it were true, we would know how many shots this basketball player is going to take until they miss. So this is not a binomial experiment. The number of shots is not fixed. In this problem, they just say, shoot until you miss. But in a binomial experiment, you need to establish before the experiment starts how many free throws this person would need to shoot. So shoot 15 of them. Okay, I'll shoot 15 of them. So that's how we could fix that. So let's move on to part B. A probability experiment in which 3 cards are drawn from a deck without replacement, and the number of aces is recorded. So is there a fixed number of trials? Sounds like there is. 3 cards, so that's the number of trials, 3 cards. So if anything, that's fixed. Are the trials independent? Will the result of one trial affect the next one? Does anyone have an intuition on this one? So there's one key phrase here. Out replacement. And the reason why that's a key phrase is depending on the first card that you choose. So without replacement means if you pick up a card, whatever card you pick up, you put that one away. You don't put it back into the deck, which means that card will affect the probability of the next card you choose because that's one less card you choose from. So this would not be a binomial experiment. Because picking one card and not replacing it will affect the probability of the next card. Or in other words, trials are not independent. So how we could fix this, that first card you pick up, you record it, put it right back into the deck, and you shuffle the deck. That would be a brand new, basically your trial will restart for the next one. So instead of without replacement, you do want to replace it. and probably shuffle the deck as well to really make sure that this would be a brand new trial. So that's how we could fix that premise. All right, let's move on to part C. A random sample of 15 football players is selected. These individuals are asked to run the 40-yard dash, and their speeds are recorded. So the first question is this experiment performed a fixed number of times? Seems like it is. 15 players. So that's the number of times this experiment is run, 15 times. So that's already established before the experiment starts, so that's good. Are the trials independent? Are the trials independent?
15 different people, so they're probably not like that long.
Well, the repercussions of saying they're not independent. So if they weren't independent, then if one person ran the 40-yard dash, then that speed would affect another person who ran the 40-yard dash. But we're assuming that these are all individual trials where the speed of one person is not going to affect the speed of another person. So these are independent. So these are, in fact, independent trials. The speed of one football player is not going to affect the speed of another. And so the next thing, for each trial, there's either a success or a failure. Is there a success or failure in this experiment? All right, since you're all very vocal about the answer, I'll just give it away. Speed is not a discrete variable. It's continuous. There's no success or failure. Generally, 40-yard dash times, if you're a football fan, you might know this, but if not, very good speed would be to run a 440, 460, 480. Looking at slower speeds if you're up to the 5-second times. But there's not really a success or a failure. Where does that threshold lie? So this would not be a binomial experiment. There's not two outcomes. Maybe there are. Anyone in here good at grammar? There is not two outcomes, or there are not two outcomes? Well, at least answer this question. There is not, or there are not? Yeah, that sounds good enough. There are not two outcomes. It's not two. Okay. So the way we could fix that is the speeds are recorded, and then you ask, did they run faster than a 470? That would turn it into a success or a failure. You could say, did they run faster than this time? Yes. Did they, well, or no? And notice how that simple addition to the experiment would turn this into a binomial experiment. And then part D down here, about 40% of US households have a gross income under $50,000 a year. And suppose 10 residents of Hammond were randomly selected and asked if their annual household income was over $50,000. So you go up to 10 people and ask them, do you make more than $50,000 a year? Or does your household make more than that? And that's recorded. So are the number of trials fixed? Well, 10 people are asked. So that seems good. So 10 residents, that seems fixed. From there, are the trials independent? Do the incomes of any person you ask, is that going to affect the income of somebody else? Not really. And finally, is there a success or a failure? Is there just two outcomes, two mutually exclusive outcomes? Well, ultimately, yes. You either make under 50,000 or you either make over 50,000 or not. It sounds like the success would be over 50,000 and the failure would be, of course, under 50,000. So this would be a binomial experiment. So this is sort of contrasting and comparing the different characteristics needed for an experiment to be a binomial experiment. Once you establish this about your experiment, then you're able to have a lot of very nice properties about your experiment that you can utilize. So from here, we can go ahead and see what these properties may entail. But first, we need to establish some notation. Because with these binomial probability distributions, the way to feed this information into some sort of, I suppose, formula or some sort of calculator command is we need three different values. Now we need the number of trials. We need the number of trials, which we normally call lowercase n. So that's the first one. We need the number of trials. And lowercase n is should be a very familiar notation. That's the sample size. That's the notation we use for the sample size, which should make perfect sense. Additionally, we use a lowercase p to denote the probability. In particular, the probability of success. So whatever success is defined in the problem, we use a lowercase p to denote that. And so a toss-up question I want to ask you all. If p represents the probability of success, then what would represent the probability of failure? Let's think about it this way. Say you have a 70% chance of winning. What would be your percent chance of losing? So that would be 30. So how'd you get 30? You subtracted 100%. Well, you did 100% minus the 70%. But when we deal with probability, we don't look at percentages, we look at proportions. So let's just move those decimals around a little bit. Instead of 100% minus 70%, it would be 1 minus 0.7, which would give you 0.3. Same idea here, 1 minus the probability. So if you have a 0.6% chance of success, how do you get the chance of, or the probability of failure? It's 1 minus that. So just wanted to say that merely as a toss-up. And since we have this capital X to represent the random variable, then what we did in the previous section is we figured out the possible values that the capital X could take on. And we looked at that as lowercase x. Now, since we're dealing with discrete values, we're going to use an equal sign, because normally the inequality, unless the context is clear, the equal sign will tell us that we're looking at just whole numbers. And we can tell this exactly what the whole numbers are. It could be 0, it could be 1, it could be 2, all the way up to the number of trials, n. Every trial could be successful, which would be the lowercase n, or maybe 3 of the trials would be successful, which x would be 3. So those are the three values we need to know in order to make meaningful predictions about this information for a particular experiment. Lowercase n, lowercase p, and lowercase x. And so with this notation established, I pass on the question, what is lowercase n, lowercase p, and the possible values of x for the binomial experiment that we found in example 1. Example 1 was the 4 situations we talked about in the bottom one. The bottom one was the one that ended up being a binomial experiment. So in that example, we need to determine lowercase n, which is the number of trials, lowercase p, the probability, and the possible values of lowercase x. What would the number of trials be in part D here? 10 residents. Yeah, it's just 10 residents. That would be lowercase n. Just 10. And there's just 10 residents. So lowercase n. What about the probability? What's that? It would be 0.4. So it says 40%, which would be indicative of probability, but we need to convert the percentage to a decimal. So it's 0.4. And then the values for lowercase x, the possible values, I'm just going to go ahead and put that one in. It's 0 all the way up to 10 because our lowercase n was 10. So the possible values we can have in this problem, anywhere from 0 to 10. Does anyone have any questions so far? If not, then, all right, so in my previous section, so I teach stats right before this class, and so the students expressed that they weren't very happy with this section of material. So this formula you see on the screen, I'm going to completely neglect it. I'm going to refer to it as just food for thought. But if we did this by hand, if we tried to determine the probabilities for each outcome by hand, this is the formula we would have to use. And part of this formula has something called the binomial coefficient, which is defined as such, but we're going to ignore all of this entirely. And instead, I'm going to focus mainly on how to do this strictly in the calculator in one step without having to touch that formula. So yes, that does imply you should probably get your calculators out because you definitely want to follow along. So we're going to scroll all the way down to example 2 here. A binomial probability experiment is conducted, and they gave us these parameters. So notice in part A, they're telling us what these values are. And so what we're going to do is figure out how to determine the probability of this binomial experiment under these specific circumstances. So they're giving us these 3 values, which I said before, these are the 3 values we need in order to plug this into the calculator. And what we're going to do is utilize a command in the calculator called binom PDF. And I'll write the general version of it. You need to put in the n first, p, and then your x value. Now, the tutorial on how to do this is in the notes. It's a little bit further back now that I decided I'm just going to skip straight to the calculator version. So it'll be all the way down here on page 56 if you have the notes printed out. So there's two situations that we could have. The situation we have is if x is equal to a specific number. That's what we have so far. When x is just equal to some number, that's when we use this first part. As you can see, the second part down here is whenever x is less than or equal to a number. We'll get to that. We'll get to that here momentarily. So what we're going to do is you have your calculator, and this should work on any calculator. So press second and 0 down here. That'll bring up the catalog. Press second and 0. And from here, you want to scroll all the way down to where you find Binom PDF. Once you find Binom PDF, this represents the binomial probability distribution function. So once you press enter on that, this should be on your screen. All these people not typing these into your calculators right now, I'm just going to trust that you can figure it out at some point. So the binomial PDF command in the calculator, once you have it here, then you need to input in order, so it has to be in order, the lowercase n value, which is 40. And then you have to separate your values via commas. So the comma is right above the 7. So 40, comma, and then it wants the probability, which is 0.99, comma, and wants lowercase x, which is given as 38. Close your parentheses. You should get exactly what I have. So this is a process we use whenever x is equal to an exact number. Is there anyone having trouble with this process? Did anyone get that number? You got it, you got it, people got it. Okay, so we'll talk about how to interpret this number later, but for the meantime, that tells us the probability of obtaining exactly 38 out of 40, whatever that may entail. Again, we'll talk about the interpretations in the next problem. Let's move on to part B, which notice the only difference in part B is now x is less than or equal to 3. And you might think that's a very minor inconvenience, but that's going to change the command that we use in the calculator. And it's all because x is less than or equal to 3 as opposed to x is equal to 38. That less than or equal to immediately means that we have to use another command in the calculator. And if you scroll down, this exact situation is highlighted in the second part down here. This is whenever you have a less than or equal to sign. We're going to treat it almost exactly the same way, but instead of binomial PDF, we're going to use binomial CDF. Binomial CDF with the same parameters. And the C just simply represents cumulative, which basically means you add up everything leading up to the final number. You accumulate all of them. So you find it in the calculator the same exact way. You go back to catalog, you scroll all the way down, and you'll see binomial CDF there. That's the one I'm going to enter. So in this problem, they tell us that lowercase n is 12. T is 0.35. Again, I'm still using commas in between my numbers. And then for the x value, we want to put the largest x value, or the one involved in our inequality, 3. And it will take care of 3, 2, 1, and 0 for us. And that tells us we get 3, 4, 6, 7. Just like that. Okay. Doing that by hand would have filled up pretty much that whole space there. So I guess it's good. Just going to skip directly to this. Does anyone have any questions about this process before we proceed? So again, we use PDF whenever we're equal to a number exactly. We use CDF when we are less than or equal to a number exactly. So let's keep going and see other situations that may come up, as well as how to interpret these probabilities. So I think I've mentioned this before in class, but Southeastern has these surveys that they post online. Some surveys they don't keep up with as much, but according to the most recent entering freshman survey, 31% of incoming freshmen reported that they live on campus. Suppose 25 of these students are randomly chosen. Well, 25 students at Southeastern, so the population would be Southeastern students. The sample would be the 25 students, and they are asked whether they live on campus or not. Their responses are recorded. Let's convince ourselves that this is a binomial probability, or a binomial experiment, rather. There's an exact number of trials already determined. So you're choosing 25 students. So the number of students they choose is fixed. Whether one student you ask lives on campus or not, that's not going to affect another student that you ask, that whether they live on campus or not. So the trials are independent. And is there just a simple yes or no answer to this problem? Yeah, it's either you live on campus or you don't. So that's a success or failure. So from here, we're going to start off by determining the probability that exactly 11 students live on campus. So exactly 11 students. So in this word problem, what they're telling us, well, if anything, from the premise of the problem, we see that the number of trials, so what's the number of trials here? That's 25, so that's pretty straightforward. The probability is 31%, so we can go ahead and convert that to 0.31. And the possible values of x, x could be anywhere from 0, 1, 2, all the way up to 25. So when they say exactly 11 students, what they're telling us is that x is exactly 11. They're saying out of those possible values from 0 to 25, I want to know the probability involving exactly 11 students. So when we have an exact equality for our binomial probability, that's when we use PDF. That's when we use PDF. Remember, CDF was for the inequality. This one's just for equality. And so they want n, which is 25. They want the probability, which is 0.31. And they want the x value, which is 11. Put that in your calculator, and it gives you the answer for free. .5, 0.31, and 11. Put that in correctly, you should get 0.0628. So simple as that. So everyone good up to here? Pretty straightforward stuff. From here, now we're going to interpret this. In 100 trials of this experiment, it is expected about blank of these trials to result in exactly 11 students living on campus. So this should seem fairly familiar to what we did in the previous section. If we know the probability and we know the number of trials or the number of times we are performing the experiment, then we can figure out of the 100 trials, we know that the probability is 0.0628. And so what this tells us, well, of course, this is 6.28. It tells us how many trials we would expect where exactly 11 students live on campus. But the number of trials is a discrete thing. It's a whole number. We have a decimal here. So we need to round this to 6 because trials are whole numbers. So 6. So if anything, I think that part should be pretty straightforward. That's stuff we did in the previous section. We're going to be doing it here a few times. Now, this is where it starts to get a little bit more complicated. This is the part that the last section was not happy with. So I'll try to be careful in how I explain this. Determine the probability that fewer than 11 students live on campus. When we had exactly 11 students, I put X is equal to 11. Fewer than 11 students, what should I put? How do we interpret that? What's that? So X is less than 11. And we can interpret the less than referring to, well, we know it's whole numbers. So the context here, we know that it's whole numbers. So we could use that as a quick notation. So it's not less than or equal to because it says fewer than 11. 11 is not fewer than 11. So we see this, and you might instantly think, well, let's go ahead and, so you might think, all right, this is the same problem as the one we did above, where we had an inequality. So I'm going to write this in red, so don't write this next part. So you might look at this and think, all right, this is the binomial CDF, because there's an inequality. You would put 25.31 and 11. This is not correct, though. There's only one reason why this is not correct. Here, this is X is less than 11. Why is that important? Because down here, it says you have to have less than or equal to. Or equal to. You have to have the equal to part, or else you can't use this process. You will get the wrong number. So you might think, all right, well, what about the situation for when it's less than X? Wait, but there's no more calculator tutorial. How do I do this? Please help. So we need to modify our inequality a little bit. So our inequality, X is less than 11, we need to rewrite that to where we have a less than or equal to sign. Does anyone happen to see how we can rewrite that as X is less than or equal to something? Just 10. If it's strictly less than 11, well, that means it could be 0, it could be 1, it could be 2, all the way up to 10. So now that slight interpretation, that slight change in interpretation means that we can now use the binomial CDF function. Because now we have the less than or equal to part with the 25, the 0.31, and now 10. Not 11, but 10. So that would be 25, 0.31, and 10. and that would be 0.8812. So notice we had to slightly modify our inequality so that way the calculator would give us the correct interpretation of the problem. And then the next part is very similar to part B. There's 100 trials. We know that the probability is 0.8812. Simply just moving the decimal place over 2 times, or if you do this in your calculator, that works too. 88.12 out of 100 trials will result in fewer than 11 students living on campus. But again, number of trials is a whole number, so we need to round this to just simply 88. Okay, is that slight change in complexity? Did that throw anybody off? Because this is where I started to lose my last section. So I want to explain this carefully. If not, maybe part E might do it. Let's find out. At least 11 students live on campus. How would we interpret that as an equality or an inequality? At least 11 students. So how would that affect an X? That's greater than or equal to 11. It's greater than or equal to 11, at least 11. At least also includes 11 as well. If it said greater than 11, we wouldn't have the equal to sign. Now, the problem here is that the sign's facing the wrong direction. If we scroll down and think about, all right, how do we do this in the calculator? Well, we have the equal to part, but we don't have the less than part. So now that's the problem. We have the equal to sign, now we need the less than sign. And again, there's no other ways this is telling us how to do it. So now it looks like we're stuck. So again, we have to figure out how to rewrite this to make it seem like, to make it seem like a less than or equal to inequality. Now, this is, I think this is the part where the students from the last section were not very happy because, well, really there's one of 2 ways you can do this. Now, by itself, we cannot rewrite this as a strict less than or equal to sign. You can't just flip the sign. You could say, well, there's 25 people in total. Wouldn't that mean that just X is less than or equal to 25? Or was it 25? Yes, it was 25. But it's also greater than or equal to 11. So these two mean the same exact thing. Just like in the previous problem, those 2 inequalities meant the same exact thing. So you basically just moved the problem elsewhere. But it's still a problem. It's still not a less than or equal to sign. So instead, what you need to do, so again, you can either tackle this problem or you can look at the complement of this problem. You can look at the complete opposite of what this problem's asking, figure out that probability, and then subtract that probability from 1. Like we did with the negative thing. So that goes back to the 70% success, 30% failure. We would look for the complete opposite probability on purpose because the opposite of greater than is less than. So we would look for the opposite one on purpose. And then once we figure out that, we subtract that from 1 or subtract the percentage from 100, and that would give us the final answer. So that's the part that the students didn't like, and I'm trying to be very careful about how I explain this. There is a compound way of figuring it out as well, which I'm going to actually do in the next part. So I'm going to reserve that off to the side. You can just pick your favorite. So instead, I'm going to write this, and I'm going to try to write it as explicitly as possible. The opposite of x is greater than or equal to 11 is what? What is the complete opposite of that inequality? So you are correct. I'm going to write it a little bit more generalized. The opposite of that is x is less than 11. You are right what you said, but we'll get to that part right after this one. The opposite of x is greater than or equal to 11 is you flip the inequality symbol, and if you had an equal to sign, you get rid of it. If you didn't have one, you throw it back in. That is the complete opposite of your sign. So if there was not an equal to sign, you would put an equal to sign. If there was an equal to sign, you take it away. You do the complete opposite. We want to find the probability of the opposite thing. And the only reason why is now we can plug the opposite thing straight into the calculator. That's the only reason why. But we can't plug the opposite into the calculator in this form. So guess what we have to do? You have to rewrite the opposite to where we have x is less than or equal to. And guess what that is? That's the 10. So that's the part we're going to find. We're finding the opposite just so we can use the calculator. And then we can subtract that probability from 1 in order to obtain the final probability that we wanted. So we're going to find the binomial CDF, or the cumulative distribution function, 25.31 and 10. But we already found this, actually. You can type it in again if you wanted. We found this in part C. That was the 0.8812. That's not the answer, though. Remember, that's the opposite of the answer. So now, this is the opposite, which means to get the final answer, we have to subtract that from 1. 1 minus 0.8812 is equal to 1 minus 0.8812, 0.1188. Or if you wanted to do 1 minus the binomial CDF, that would have worked as well. But this is a process you will have to use if your inequality is facing the wrong way. This is a process you will have to use, because the opposite will give you the correct facing side. And part F, if anything, part F should be straightforward. There's 100 trials, and we figured out that the probability is 0.1188. So that's 11.88. So there's 100 trials, they tell us, and the probability from the last part was 0.1188, and that rounds up to 12. So 12 of the 100 trials would result in at least 11 students living on campus. Did I lose anybody with that? Part G also has a little bit of trickiness to it as well. Determine the probability that between 9 and 11 inclusive live on campus. Now, what is that as an inequality? between 9 and 11. There's a 9, an 11, and there's an x that's in between it. So that's what the inequality, inclusive means that we're including them, of course. So what we need to do from here is figure out, well, how do we figure this out? This is a compound inequality. We don't have anything that tells us how to deal with compound inequalities. So once again, we need to be very clever about how we rewrite this, if we can. Now, what makes this problem difficult is because this is a compound inequality, then we're going to have to split this up into two. So really what we have is x is greater than or equal to 9, and x is less than or equal to 11. So we have two things going on here. And one of them we could figure out really quickly. The other one, not so much. So this is what we need to do. And I think I thought of a good way just now on how to explain why we do this. I guess I'll write it down here. So this isn't what goes down here, but doing this for illustrative purposes. With numbers, with arithmetic, when we subtract 0, 1, 2, 3, 4, 5, 6. When we subtract, how does subtraction actually work? If we're subtracting 6 minus 4, what are we actually doing here? Well, 4 is the difference from 0. 6 is the difference from 0. And really what we're doing is these differences here, we're trying to find the difference between those two right there to figure out this little part in the middle. And you might think, why the heck are you talking about this? I thought we were doing binomial stuff. This illustration is why we're going to do binomial CDF involving the 11, the larger number, that'd be 25.31, the 11, because it does have the equal to sign, but we're going to subtract the binomial CDF of 25.31 and 9, the second one. And that might seem a little strange, but if we're trying to figure out the probability between, what we're doing is we're figuring out the larger inequality, the segment of that, or the probability, and subtracting that from the smaller one. That's sort of the illustration behind why this is the case. Or if you just want to memorize between means you subtract like this, then that's perfectly fine. And so what this is going to do is this difference will give us the remainder between the 9 and the 11, inclusive. Actually, I think that 9 should be an 8. 10, 11. We can actually check that momentarily. I think that should be an 8. Because we're doing the opposite of this. And I know a way to check this right fast, just to make sure that this is correct. So in fact, let me do that first. I want to check that this does work. Yeah. 1 and 9. That's okay, and 1. Okay, so I believe that should be 8. So let's find out if that's true. So in the calculator, I'll just go ahead and clear all of that out. This would be binomial CDF 25, 0.31, 11, minus, pretty much the same thing, 5, 1, and 8. Oh, okay, that was right. .3079. Again, notice how we're breaking down the compound inequality into two separate inequalities. One of the inequalities is pretty simple. We can plug that in directly, as we did over here. But the reason why we're subtracting by the second inequality is because we did the opposite. And the opposite doesn't necessarily mean we have to subtract by 1. Since we have an upper bound, we're subtracting from that upper bound. So that's where the second one comes from. And remember, we're going down to 8 instead of staying at 9 because the opposite brought us to x is less than 9, but we needed an inequality, so we bumped the 9 down to an 8. Finally, in 100 trials, see that the probability is 0.3079, which is 30.79, which we can go ahead and round that to 31. Does anyone have any questions about that one before we move on? If not, we can also determine the mean and the standard deviation of a binomial random variable. So the mean and standard deviation, these are some pretty straightforward formulas. Sometimes they use either one of these two formulas to represent the mean. And it's just saying that the expected value is just your sample size, lowercase n, times your probability. And then your standard deviation is the square root of, well, really your mean times the failure probability. So those are pretty straightforward formulas. So let's move on to example 4, which will bring up some familiar stuff. And we can also figure out the mean and the standard deviation. So they tell us that n is equal to 5 and p is 0.2. So let's go ahead and, so for this problem, they want us to construct a binomial probability distribution with the given parameters. And notice they're using lowercase x. So for each row, what they're wanting us to find is when x is equal to 0, or when x is equal to 1. X is equal to 2. So really, since this refers to x is equal to 0, and that refers to x is equal to 1, and so on, then we're going to use the PDF option, where they told us that lowercase n is 5, lowercase p is 0.2, and lowercase x is 0. And how each one of these changes is simply the lowercase x value that we have. So this part should be pretty easy so far. Five, 0.2, and I'm using the PDF and not the CDF. PDF is when we are exactly equal to a number, and 0 would be the first one. 0.32, I do 77, around the 4 decimal places. And you don't have to keep typing this in the calculator. If you want to retrieve the last entry in your calculator, you could just press second and enter. All you have to do is move your cursor around. You don't have to keep retyping it every time. So I'll replace the 0 with a 1 for the next one. 0.4096. And then again, second enter. So I don't have to type it again. 2. So I'll bring up a few. 3. Okay, that's the next 2 then. 0.2048, 0.0512. 2. 4. I'll go ahead and get 5 out of the way. 0.64. The final ones in scientific notation. Oops. 3.2 e to the -4 just means you move the decimal place over 4 times to the left. 1, 2, 3, 4. 0.00032, which has 4 decimal places. That's just 0.0003. So that's a quick way to knock all of those out, because you will have a homework question similar to this, and as long as you know how to do it quickly, you can knock that out in 2 minutes. Now it goes on to ask for us to determine the mean and the standard deviation. The mean is simply n times p. N is 5. P is 0.2. It's as simple as that, which I believe is just 1. Let's check and make sure. 5 times 0.2. You're taking a fifth of 5, so that's just 1. So that's the mean. Pretty simple formula. The standard deviation, a little bit more intricate of a formula. So that's the square root of n. Oops, I can put in actual numbers now. N is 5, p is 0.2, 1 minus 0.2. Whatever that number is, will be our standard deviation. Square root, 5 times 0.2 parentheses, 1 minus 0.2. Close parentheses, close parentheses. 8944. Okay. So those formulas should be pretty straightforward. Does anyone have any questions before we move on? If not, there is a note that I want to make regarding the binomial distribution. This is an important note. As n increases, the binomial distribution becomes more bell-shaped. That could be a pretty easy question for me to ask on the next exam as one of those true or false questions. Or as n increases, what happens to the binomial distribution? And then you just say, it's more bell-shaped. So this basically goes along, this correlates with the law of large numbers, that the more times you increase your repetitions, well, this talks about how normalized the information spreads. If you think about a histogram, then you might think about it as you would get more expected values in the center, and they would space away from the center very symmetrically. Now, we can use this information to mention where this bell shape is approximated. Remember, statistics never makes anything exact, but when the distribution is approximately bell-shaped, then we can use the empirical rule. 95% of the outcomes are in between two standard deviations of the mean. That's 68, 95, 99.7 rule. We use the empirical rule whenever that particular product, NP times 1 minus P, is greater than or equal to 10. So let's look at example 5 and see how this is applied. So again, on Southeastern survey page, they have a report that they released called Southeastern Cares, and 49.2% of students, these weren't necessarily incoming freshmen, but just students who took the survey, I believe it was about 500, reported that they live with their parents still. So if 300 students are randomly selected, how many would we expect to live with their parents? Well, this should be pretty familiar. 300 students. And we're already given the probability over here, and we can figure that out fairly quickly. 300 times 0.492. 147.6. But we're dealing with students, which are whole numbers. 148 students then would be expected to live with their parents. Now part B talks about a data being unusual, which sounds like an outlier, but we're not really dealing with outliers in this case. We don't have enough information to determine fences. That means we need to have raw data or the 5-number summary. So, and if you haven't made the correction already, a random sample of 300 students, not 200 students. So would it be unusual to observe 250 students living with their parents? What they define as unusual means more than two standard deviations away from the mean. as mentioned in the note that's at the top here. 2 standard deviations away from the mean. So in order to figure out if 250 is unnatural, we need to figure out ultimately its z-score. So the z-score of 250, well, we can't figure it out yet because we don't know the mean or the standard deviation. But that means we hopefully should be able to figure it out. So we need to know the mean, which is just n times p. The number of people surveyed here is 300. It's not the 250. That would be x times the 0.492, which is actually what we already figured out. That's how many we would expect to live with their parents. And then the standard deviation was the square root of np times 1 minus p. N was 300. P is 0.492. 1 minus 0.492. So square root 300 times 0.492 times 1 minus 0.492. And that tells us that the standard deviation is 8.66. I'll leave it at 2 decimal places. So now we can figure out the z-score right fast of the 250 students to see is that unusual or not. So the z-score is the value itself minus the mean divided by the standard deviation. So let's figure out the z-score of this thing. 250 minus 148 divided by 8.66. So I think that goes to show for itself a z-score of almost 12. That's insane. So that's greater than 2. So this is unusual. Because it's greater than a standard deviation of 2. If we had a standard deviation less than 2, then it would be usual. It would be within the 95% expectancy. Now, I'll go ahead and wrap it up here. There's not really much I can get accomplished in the last minute. But if you do need to talk about your exam, you can schedule office hours with me or shoot me an email asking about your exam. Besides for that, don't leave with your exams. Please set them on the desk here. Homework due tonight, and that's all I have. Have a good day.
I have a question about